Hello students, welcome you all to next session regarding discussion of the generalized flow machines, a continued part. In the yesterday's session, we have discussed regarding the radial flow machines, the outward flow machine, radially outward flow machine, radially inward flow machine. We have seen that in the radial outward flow machine, the radial inward flow machine, what are the changes in the velocity diagrams, and generally for the power absorbing machines, they are nothing but they are the radially outward flow machines, which means the flow of the fluid is moving away from the central from the axis of the shaft, which means it is the case of an power absorbing machines. In today's session, we'll be discussing regarding the effect of blade discharge, and blade discharge angle for the energy transfer as well as the degree of reaction. So the blade discharge angle is a thing, but it is the value of beta 2 for the three cases. That is, with if it is an acute angle that is less than 90 degrees, equal to 90 degrees, and greater than 90 degrees. So as we move ahead, we'll be discussing all these things in today's session. So if you have any doubts, you can send me an email to this email IDs, which you can see on the screen. Also, you can send me a message to this WhatsApp number also. So apart from that, you can subscribe my videos on the YouTube channel, where when I go on posting the new videos, they will be intimated to you directly itself once you subscribe my particular videos. Okay, with all these things, we shall begin the today's session now. So please watch the video carefully, because it is a very, very important part. So the title is the effect of blade discharge angle on energy transfer, or sometimes it is given in the form of a statement also, that is a radially outward flow turbo machine which has no inlet whirl. The blade speed at the exit is twice at inlet. Then the radial velocity is constant throughout. Taking the inlet blade angle as 45 degree, and beta 2 is equal to beta 2 is the blade angle at exit with respect to the tangential direction. Show that the degree of reaction R, it is equal to 2 plus cot beta 2 by 4. These are the conditions given, and you need to prove that the degree of reaction R is equal to 2 plus cot beta 2 by 4 in the form of statement, or else in a form of a heading, that is effect of blade discharge angle on energy transfer, which we will be discussing right now. Before we start the things, let us read the statement given to us very carefully. So initially he has said there is a radially outward flow turbo machine. Radial outward flow turbo machine means it is a case of an power absorbing machine. Yesterday we have discussed the fluid moving away from the center of the axis. So it is nothing but it is a power absorbing machine. Means example for the pumps, fans, blowers, compressors, they are all the power absorbing machines. Then he says there is no inlet whirl. So when you draw your inlet velocity triangle, please see here, this is your generalized inlet velocity triangle. You can see on the screen. This is your inlet velocity V1 with angle alpha 1. Then we have the flow velocity Vf1. Then we have the relative velocity Vr1. And apart from this, we have the angle, that is beta 1. Then we are having the tangential velocity, that is tangential component of the absolute velocity as Vu1. This is the angle. And finally, we are having the tangential velocity, or you can call it as even the blade speed at the inlet. Now we have drawn with respect to the inlet triangle. He says in the statement that there is no inlet whirl. So here the inlet whirl is nothing but it is the factor, that is the Vu1. He says there is no inlet whirl means Vu1 is equal to 0. When Vu1 is equal to 0, then this term V1, it overlaps on Vf1, and the new velocity triangle, it looks like this. Please see here. This is the new velocity triangle. So this is nothing but Just I am drawing here for understanding purpose. This is your new velocity triangle. So now I have said that both are overlapping with one another. That is v1 is equal to vf1. Then the remaining things as usual. That is, this is vr1. Then we have the velocities u1 with angle beta 1, and here I have said vu1 is equal to 0. Another important thing is he has said the inlet blade angle is 45 degree, which means this particular angle is 45 degree. Do you agree with this point? So when the inlet blade angle is 45 degree, even the other side, that is this side, the third angle, this is also 45 degrees. And another important thing is now here the angle alpha 1, it is equal to 90 degree. It is equal to 90 degree. Please see here. This we have shown that this is our tangential velocity u1 with an angle how much? 45 degree. Similarly, the other side with the flow velocities vf1 and v1, it is making an angle of 45 degrees, which means according to this figure, what you can state? You can state that u1 is equal to vf1 is equal to v1. So once again, I will draw the sketch. Please see here. Once the new inlet velocity triangle is drawn with the given conditions to us, it looks like this. So as the overlapping has happened, v1 absolute velocity is equal to flow velocity at inlet, that is vf1. Then this is your alpha 1, which is equal to 90 degrees. Then this is our relative velocity vr1, which is making an angle of beta 1, and this value is already as told inlet blade angle is 45 degree, which means beta 1 is equal to 45 degrees, which is made by the blade velocity, that is u1, or you call it as the tangential velocity at the inlet u1. Now if you observe here carefully, the third angle that is here, this is the third angle which is made between the v1 and vr1. This value is also equal to 45 degrees, which means both these two sides u1 and v1, they are similar to each other, which means I can write this as v1 is equal to vf1, which is also equal to u1. Please see this carefully. Okay, so these things we have proved. These things has no inlet velocity, which I have shown here, which means vu1 is equal to 0. Then the next statement given to us is the blade speed at exit. The blade speed at exit means it is u2. It is twice that at inlet, which is equal to u1. Then the next thing he has said is the radial velocity. It is constant throughout. He has said that the radial velocity is constant throughout, which means the radial velocity is nothing but it is vf1, which is equal to vf2 for both inlet and outlet. And he has said throughout it is constant, which means it is equal to vf. Okay. So with these things, we need to find out the value of this particular derivation, that is r is equal to 2 plus quad beta 2 by 4. So even it may be given in the form of a statement or even in the heading. So if it is given as the heading, you need to make all these assumptions which just now we have stated in the statement. So let us see what are the assumptions they are making. I said consider a parametric effect of the discharge blade angle on the energy transfer and degree of reaction with making some assumptions. The first assumption which he has said to us is the tangential velocity of the rotor. Tangential of the rotor at exit is double that at the inlet, which means U2 is equal to 2U1, which is already given in the statement also, the first assumption. Then the second assumption he has said the radial velocity is constant throughout the picture, which means Vf1 is equal to Vf2 is equal to Vf. The third thing is the fluid enters radially. Yes, very, very important. The fluid is entering radially. Radially means it is entering radially. When it enters radially, there is no whirl velocity, which means V1 equal to 0, which means these are the conditions. These are the conditions for the fluid entering radially. Alpha 1 becomes 90 degrees, V1 equal to 0, and also Vf1 is equal to V1, which is also equal to the constant velocity, that is radial, that is Vf. And the fourth point he has told that the blade angle at the inlet is 45 degrees. So when this is the case at 45 degree, the two sides become the similar sides, and automatically V1 is equal to Vf1 is equal to Vf2, which is also equal to U1. These are the things you need to remember before you start the analysis. Now, let us begin with the analysis. So this is the inlet velocity triangle, because the conditions you can see here, the value of V1 is 0, which you can see here right now on the screen. Also, he has said that beta 1 is equal to 45 degrees, which means even this angle is also 45 degrees. And in some textbooks, he has given Vm, but both V1, Vm1, and this is nothing but it is also equal to Vf1. So both are equal, both are nothing but in some textbooks it is taken as Vm1 or it is Vf1, all the same itself. Now, moving ahead. Initially, the outer velocity triangles, I said we are discussing regarding the energy transfer, and this we are discussing on the blade discharge angle effects. So there are three cases: beta 2 less than 90 degrees, beta 2 equal to 90 degrees, beta 2 greater than 90 degrees. So now if you observe this first picture here, in this first picture, if you observe carefully, especially in this right angled triangle, the value of beta 2, if you observe, it is lesser than 90 degrees. This is the first case. Second case, if you observe carefully, yes, now if you observe carefully this triangle, what is the value of beta 2 here in this case? It is equal to 90 degrees. Similarly, if you observe the third case, here, if you now observe carefully, what is the value of beta 2 here? It is greater than 90 degrees. So all these three cases we are going to study now. So in the examination also, you need to draw the sketch and their position in this form itself, because it becomes very much easy for the analysis part. Okay, students. Now let us move further. So initially, you know that the radially outward flow machines are nothing but they are the power absorbing machines. And for this, the energy equation, the Euler's energy equation, we are writing it as U2 VU2 minus U1 VU1 by GC. The equation I have written, which we have discussed in the yesterday's, in the previous session also, which we have discussed in the previous session also. So as our inlet velocity triangle, if you observe, it is having no whirl velocity. As our inlet velocity triangle, it doesn't have the whirl velocity V1 is equal to 0. Then I'm substituting what I get the equation, I get it as U2 VU2 by GC. Now what I need to find out? I need to find out the values of the velocities. So let us see how we can do this one now. I have taken the previous session's sketches itself for the outlet velocity triangle. This is our outlet velocity triangle. This is our outlet velocity triangle, that is O, A, B. I need to find the value of AC, that is VU2. VU2, how I can write? I can write AC as something, but it is AB minus BC. The things I have taken, AC is equal to AB minus BC. What is AB? It is the tangential velocity U2, BC. But for BC, what I do to know again? For BC, what I am doing is I am taking the help of this particular right angled triangle, this one, that is OCB. So for OCB, what I will find out is I will find out cot beta 2. If you take it carefully, cot beta 2 is nothing but it is the opposite side, BC divided by OC, or BC is equal to, I can write as OC cot beta 2, which you can see in the equation which I have written now. So it is nothing but AC is VU2, which you can see here, OC is cot beta 2, OC is nothing but it is the flow velocity Vf2 cot beta 2. So which it means that we have got the value of VU2, and you can substitute this in this equation to get the value of energy equation. E is equal to u2 vu2 minus vf2 cot beta 2 u2 into bracket u2 minus vf2 cot beta 2. This is our equation number 3. Now, these are the assumptions which we have made. That is u2 is equal to 2u1 is equal to 2vf1 is equal to, and another thing is the flow velocity is constant throughout. That is vf1 is equal to vf2 is equal to vf. Okay. So how this condition is satisfied regarding this 2u1 is equal to 2f1, because in the inlet velocity triangle we have said that our angle beta 1 it is equal to 45 degrees. Beta 1 is equal to 45 degrees. So automatically even this angle is also 45 degrees. So therefore this is the value of u1, and the same similar side we are having even v1 also, which means v1 is equal to u1. So in the statement he has said that the value of u2 is equal to 2u1, and now using this particular statement u1 is equal to v1, that is nothing but it is 2v1, and this v1 it is also equal to which one, the flow velocity here. So therefore it is equal to 2vf1 also. So just now we have derived our energy equation. What is our energy equation? Energy equation is E is equal to, it is u2 by gc into bracket of u2 minus vf2 into cot of beta 2. This is our energy equation which we have derived. Please see here carefully. Now what I will do is, whatever other velocity terms are there, that is the tangential velocity u2 inside and outside the bracket, I will replace them in the form of the flow velocity vf2. So u2 is equal to what? As you can see here, it is equal to 2u1, and this 2u1 is equal to vf1, or it is also equal to vf2 itself. So what I can write it here as u2 is equal to 2u1, then it is equal to 2vf1, or it is also equal to directly it as 2vf, because all vf1 vf2 is equal to vf itself. So this term on this vf2 it gets substituted as vf only. Now let us see here what we can do now. So now what I will do is I will simplify these terms, and whatever the equation you are seeing right now here, the energy equation, I am going to substitute the value of u2 in the form of the flow velocity. Let us see what we are going to get now. Yes, as I told, u2 in the form of u2 is equal to 2u1, that is equal to 2vf2, vf2, and these are all flow velocities, that is the radial velocity, it is constant throughout. So vf2 is equal to vf1 is equal to vf, which means I am reducing this equation. Here what I am doing is I am taking this vf2 as common, which becomes 2vf2 square, and totally it is again satisfying this condition, that is vf is nothing but it is equal to this particular thing, that is whatever the vf2 you have got, it is nothing but it is equal to vf itself. So directly I have written this one, that is 2vf square here. So therefore our equation number 4 is 2 into vf square by gc into 2 minus cot over 2. But if you observe here carefully, as this is the flow constant equation, that is our vf square by gc, this term it is a constant term, its value is very less, so you can neglect this particular term. So if I neglect this particular flow velocity constant, then the equation 4 it becomes as E is equal to 2 into 2 minus cot of beta 2, 2 minus cot of beta 2. Now I can write the Euler's energy equation in the form of the velocity components. You know, we are writing it as the kinetic component, that is centrifugal component, and the reactive component for the power absorbing machines. Please keep in mind we are writing for the power absorbing machines, which means our initial term will be v2 square minus v1 square by GC. Similarly, we are having the other terms, that is u2 square minus u1 square by 2 GC plus VR1 square minus VR2 square by 2 GC. Now, this is our equation for the velocity components, energy equation in the form of velocity components, which you can see on the screen. Next, our degree of reaction equation. So degree of reaction equation in the simplified form for our velocity energy equation, we can write it as R is equal to, in the form of energy, that is E minus of, we can write it as V2 square minus of V1 square by 2 GC whole divided by E itself. So therefore, you can write this is as our equation number 5. So in the initial statement itself, we have said we need to find the value of R is equal to the constant term, that is R is equal to 2 plus of carbon 2 by 4. We need to find that one. So what we can do now here is we have this equation 5, and what we will do is we will find out all these terms one by one, which are we need to find the value of E. Also, we need to find the value of this entire term. So those are the things which you are going to find now. So let us move ahead. So again, we take our inlet velocity triangle with the condition that there is no whirl velocity, which means V1 is equal to 0, alpha 1 equal to 90 degrees, V11 is equal to Vf1, which is equal to U1. And now from the inlet velocity triangle, as I said, V1 is equal to Vf1. So therefore, the condition for the outlet velocity triangle, we begin with the first condition, that is beta 2 greater than 90 degrees. So this is the triangle beta 2 greater than 90 degrees. Please observe here carefully. This particular triangle, when beta 2 is greater than 90 degrees, this is the triangle we are going to consider for our analysis. And here we are applying the cosine rule. So the cosine rule, how we apply, that is beta 2's opposite side is V2 square. V2 square is equal to the sum of the square of the other two sides, that is this particular value. This is nothing but it is U2 itself, it is U2 square plus VR2 square minus of 2U2 VR2 into cos of beta 2. We are applying this particular cosine rule right now. So we are applying that cosine rule, which you can see here right now, minus 2U2 VR2 into cos beta 2, which we have applied right now. Next, we go for the analysis of this particular equation, and we are simplifying this VR2 square as this particular form, that is Vf2 square by sine square beta 2. Also along with this one, wherever VR2 is there, we are replacing this term. How we are going to replace? For the replacement of this particular term, what we do here is we again consider the next case, that is beta 2 less than 90 degrees. We consider the next case. This is our next case, beta 2 less than 90 degrees. So when our beta 2 is next to 90 degrees, so if you observe this particular sketch here, this is the triangle. So now here, how I can write a sine beta 2 here, sine beta 2. Sine beta 2 is equal to, the opposite side is Vf2, and from the tangential velocity, the relative velocity, it is nothing but it is the value of in the form of the relative velocities. So I can write, sorry, it is nothing but Vf2 by Vr2. We get the opposite side by the hypotenuse. So now Vr2, what is the value of Vr2? I can write Vr2 is equal to Vf2 by sine beta 2, which I have simplified here directly. So on simplification, you can write VR2 as nothing but from this particular triangle. Once again, I'm saying from this particular triangle, sine beta 2 is equal to, opposite side is Vf2, the hypotenuse is Vr2. We need the value of Vr2. So Vr2 is equal to, it is Vf2 by sine beta 2. Here it is Vr2 square. So what I will do is I will square this one, which means it becomes Vf2 by sine beta 2 whole square, which I have written directly here. So please take care that Initially, when I am writing the cosine rule, I am applying the condition for cosine rule. The condition which I am going to apply is beta 2 greater than 90 degree. But once I want the replacement for VR2, when I want the replacement for VR2, I am applying the condition of beta 2 less than 90 degrees. So if you make this adjustment, you will get the equation in the required form. So now, what you can see here, this is the thing. And as I said, for outer triangle, beta 2 is less than 90 degrees. Sin beta 2 is equal to V of 2 by VR2, which we have done with the replacements. So now from here, we need to do our simplification part. Simplification. Cos beta 2 by sin beta 2 is nothing but it is cot beta 2. Then your terms are there. 1 by sin square beta 2 is nothing but it is cosec square beta 2. And we will replace the terms here now. That is, we are replacing u2 in the form of 2u1, which is also equal to 2v of 1. So now it is u2 square. It is u2 square. So means squaring of this 2v of 1 is nothing but it is 4v of 1 square, which is v of 1 equal to again v of. So directly we can write in this form also, that is u2 is equal to, it is 2u1, which is given, but here what it is u2 square. What I will do is I will square this one. So this is the square of this one, which becomes 4u1 square, which is also equal to 4vf1 square, which is equal to nothing but it is 4vf, because throughout the radial flow, the velocity of flow is constant itself. Directly I will write, or you can make stuff, go for another 2 steps also. So I have written directly now, that is 4v square vf square plus vf square cosec square beta 2 minus this one u2 is nothing but again it is 2vf into it is 4vf, and another vf2 is already is there, which we will square, which will multiply, and we get it as 4vf square into cot beta 2. So your trigonometric function cosec square beta 2 is nothing but it is 1 plus cot square beta 2. I use this equation here such that we get it in the form of the cot beta 2 on both sides. We multiply the v square f, this v square f which you are observing here. I will open this v square f. I will multiply inside this brackets, and on multiplication, I get this equation now. So 4v square f, this v square f, I add up, and I get it as 5v square f plus vf square cot beta 2 minus 4v square f cot beta 2. That is the value of v2 square. Or if I take vf square as common in all the terms, it is 5 plus cot square beta 2 minus 4 cot of beta 2. So this is v2 square. In our equation, of degree of reaction, what was our degree of reaction equation? R is equal to, it was E minus of v2 square minus of v1 square whole divided by 2gc upon whole divided by, it was E, right? Regarding this E, we have derived the energy transfer equation there itself. Now we have got the value of v2 square. We need to find the equation of v1 square. We are proceeding now in this manner now. So we have substituted the value of v2 square as here. So the value of v2 square, whichever is there, this v2 square we have substituted here, and v1 square is taken here. Now the simplification part, it begins like this. Okay, so v1 square is nothing but v1 is equal to vf1 is equal to vf itself. So v1 square directly I will write it as vf square. Okay, so now if you observe in the numerator, the vf square term is common. I will take it out, which means it becomes 5 plus cot square beta 2 minus 4 cot beta 2 minus of 1. So here 5 minus 1 is 4. We get 4 plus cot square beta 2 minus 4 cot beta 2. Then if you now see, we are getting in the form of v2 square minus v1 square by 2gc. We have got this value. We have got the value for v2 square minus v1 square by 2gc. Now what I will do is, our degree of reaction equation, what it was, R is equal to E minus of v2 square minus v1 square whole divided by 2gc upon, it is E. So regarding this E, the energy equation we have already derived in the third equation itself. That is energy E is equal to It was written in terms of the factor of VF itself. We had written it as what was the term written? It was written in the form of 2VF square by GC into 2 minus quad by 2. Okay, that I am going to write directly now here. So now on simplification, it was 2VF2 into this energy. This is the value of our energy equation which you have derived previously itself. At the starting of this class, we have derived this equation. This is nothing but it is the value of E, and this is also the value of E itself. Then this is the value of V1 square minus V2 square. Okay, this is our equation. Now simplification part. So what you can see here carefully is VF square and by GC it is common on both numerators and denominators. It gets cancelled. Then our remaining equation, it is nothing but 4 minus 2 quad by 2 minus 1 by 2, 4 plus quad by 2 minus 4 quad by 2. So what you can do is, here you multiply the numerator and divide the denominator by 2. I am multiplying this entire equation on the RHS side, multiplying by 2 and dividing by 2, which means no change. Why I am doing this one, I will let you know, because we need the required derivation in the form of the degree of reaction which he has asked to us. So therefore, R is equal to 8 minus, I have multiplied in the numerator side by 2. So it is 8 minus 4. Then here what happens, it gets cancelled here. That is, I have opened the brackets, it becomes minus 4 minus quad square by 2 plus 4 quad by 2. At the denominator, I have kept the same itself. So therefore, now if you observe here carefully, minus 4 quad by 2 plus 4 quad by 2 gets cancelled. 8 minus 4, 4 is remaining, which means in the numerator part, I get the equation as 4 minus of cot square beta 2 divided by 2 of 4 minus 2 cot beta 2. If you observe this term carefully, it is in the form of a square minus b square, which is nothing but it is equal to a plus b into a minus of b, right? Now, what I will do is, R is equal to 2 plus cot beta 2, that is a square is 2 square minus b square is cot of beta 2 whole square. 2 plus cot beta 2 minus cot beta 2, these two gets cancelled. And the remaining question is this one, which he had asked us to prove this as. So, therefore, this is the effect of discharge angle, blade discharge angle for the power absorbing machines, which you can see right now here. Okay, and also we have proved the value of R is equal to 2 plus cot beta 2 by 4. So we shall stop today's session here itself. In the next session, we will be discussing regarding some of the axial flow machines also. Okay, so we will be discussing as we move further. Okay, students, we shall stop here. Thank you.